Hey, good afternoon. I don't know if you want to wait for a couple of seconds for everybody to join. So welcome to the last panel. So the announcement is we have our fourth participant from Trimble. Mr. Ed Jones is joining our panel. Let me start with our first presenter, Professor Naser El-Sheimy, professor at University of Calgary, and also he started a couple of years ago, Trusted Positioning, and he holds CEO position in that company. And without further ado, I'll actually turn the floor to him.
Thank you very much, Farshid, for the short introduction.
I can make it longer next
No, no, this actually was my request. So I saw that you were only 3 people, so I was targeting 20 minutes, but I have to speak fast. The good thing that when you speak the last session that you can definitely skip some of your slides because they either have been covered or have been already covered in some of other presentations. So my presentation mainly focus on sensors, and more specifically MEMS sensors, and what are the promise of these sensors for location, navigation applications and location-based services. So one of these slides, the first 2 slides, I'm just going to go through them very quickly. There is no question that RF technology have been witnessing a revolution over the last decade. We have been seeing new signals, for example, for civil signals in GPS. We have seen new satellites such as Galileo. We have seen also new alternative GNSS such as the ISM that has been presented today. So the net effect for the user that with new satellites we'll have more signals, we'll have, of course, better geometry and better availability and accuracy. But of course, the physics is physics. There is so many limitations that has not been even looked at, in more details, and also there is some problems that we still cannot overcome. For example, in GNSS, availability is a big issue, specifically in urban centers, and of course, inaccuracy due to multipass. In wireless signals such as Wi-Fi and cell lock, we still have the infrastructure, as many of you mentioned today, is expensive and not always present. And also there is sparse network, which is either or poorly surveyed networks that definitely affect the accuracy for indoor navigation applications. On the other hand, we have what we call self-contained sensors. Self-contained sensors are sensors that does not require any external signal. And the most commonly, sensors in this category are inertial sensors, which typically include accelerometers and gyros, which also have been witnessing a revolution over the last, I would say, 30 years. Starting, let's say, in 1980 with bulky systems that are based on what we call ring laser gyros, that at that time, I think in 1980, I still remember the first system I worked with at the University of Calgary. This was actually late 1980s. Late 80s. It was costing about $300,000. It was from Honeywell. Then we started in 1990 seeing what we call fiber optics, gyroscopes and fiber optic systems that costing around $60,000 at that time. However, their price are coming down to $20K. Of course, these systems are still expensive for many consumer applications. However, I must say that still fiber optic gyros are potential for indoor mapping that can lead to map that can be used for indoor navigation applications. It took us about, I would say, 40 years to come down to what we call micro machine sensors that are costing $1 and less, and even having complete system in a chip that can be integrated in smartphones. No wonder we start seeing many of these sensors in many of our day-to-day life, what you call devices such as smartphones, BDAs, and cars. Of course, MEMS sensor has been used in cars a long time ago for non-navigation applications such as airbag deployment, stability of cars, and so on. However, in smartphones, the sensors has been integrated also in the portable devices also for other reasons, such as, for example, power control, switching on the screen, and so on. But I must say that there is definitely a promise of this sensor that they can also be used for navigation. If you look, for example, in some of the smartphones that has been released in the markets in the last few months, for example, the Samsung Galaxy Note. The Samsung Galaxy Note contains already 3 gyroscopes from ST Micro, 3 accelerometer from Kionix, 1 Bosch parameter, 1 GPS from Broadcom, plus, of course, high-resolution cameras. With all these sensors, we have what we call over 8 degrees of freedom that can also be used with GPS in order to bridge the GPS in areas such as urban center, but also can be used in what you call it in indoor navigation. So the real question is, since sensors already exist in these phones, why we have not seen so far a navigation application that can really take these phones into indoors up till now? I think the answer to these questions has many folds, and I will try just to give you some of the challenges from my perspective and from my trusted positioning perspective that has been affecting the use of these sensors in indoor navigation. The first one have to do with what we call usability. Typically, I'm sorry, I'm not quite sure why it's jumping. Probably I'm pressing on something here. The first one is have to do with the usability of portable devices. You cannot really control the user or the consumers. Consumers typically want to use the phone in any direction. I think Frank, and unfortunately maybe he left, he showed the video in the morning that I think the smartphone was used for car navigation as well as an indoor navigation. But what Frank did not mention is that the phone was actually restricted to one direction, which is mainly the front direction of the the front direction of the user, and also it was fixed in the dash of the vehicle. When we start using smartphones in our day-to-day navigation, we cannot ask the user to do that for many reasons. Of course, 50% of smartphone users are young kids. They will never listen. There is no manual actually they can read for the smartphones, and therefore, the end requirement is mainly for the orientation and the position of the vehicle or the person, not the phone itself. And therefore, the software that have to operate and manage the sensors have to be smart enough to detect the orientation of the user and the orientation of the vehicle, not the orientation of the phone itself. So this is one of the constraints, or one of the challenges. The second challenge is, again, smartphones will be used by people. These people will be walking, they will be driving, they will be riding a bus, they will be riding their car, and so on.
It actually went to the next one.
Oh, I'm sorry.
It might be the papers.
Yeah, it's okay. So, unfortunately, most, if not all, the navigation algorithms being used to date are platform-specific. If you look again at the video that have been shown by Frank in the morning, the phone was fixed in the dash, and by doing so, you are fixing the orientation between the user and the vehicle, right? And the reason for that is that this triggers a specific algorithm to be used in vehicles only. When you use it, for example, we use the phone for BDR, or what we call dead reckoning, pedestrian dead reckoning. Typically, most of the software require the phone to be fixed on the belt of the user, or to be handheld in front of the user. And therefore, again, these are trigger a certain algorithm that use a specific accelerometer to detect the steps of the user. However, again, in consumer application, we cannot restrict the user, to mount the sensor in a certain direction. At the same time, we cannot restrict. We need to detect exactly which mode of conveyance the user is going through, and therefore, optimal algorithms are needed to detect whether the phone is being used in walking, or being used in a car, or being used in a train. So this is another challenge. The third challenge has to do with the sensors themselves. The sensor typically any sensor contains errors, right? And the second issue with the sensors themselves is the physical laws that we use for estimating the navigation from the sensors. Most, if not all, inertial navigation systems are based on integration. Integrating acceleration gives us velocity, integration velocity gives us distances, and integrating gyro measurement gives us angles. Integration, by definition, means summation. So if you start with an error, you're actually summing these errors. And therefore, these errors will be accumulated, and this will end up with what we call drifted position. And therefore, And even this accumulation of errors is even worse in the case of MEMS sensors when compared to fiber optics and ring laser gyros. And therefore, advanced sensor modeling is needed in order to deal with the high drift of this sensor. Just to show you an example, this is, for example, a vertical accelerometers in static mode that cost about $2 to $3, typically used in some of the smartphones. If you put an accelerometer in vertical mode and static, the only force acting in that is gravity. And therefore, you expect that the accelerometer measure 9.8 meters per second square. If you look at this, you find that you have a bias. First of all, you have a constant error, which is about 50 milli-G. This is very, very large error. If you integrate that, it will give you hundreds of meters in maybe a few seconds. The second thing, you also noted that you have some sort of correlated noise, right? And therefore, you need to model that inside the fusion algorithm. The correlated noise of the MEMS sensors are much more severe than the fiber optics and mechanical system or mechanical accelerometers. And therefore, again, we require smart techniques in order to be able to account for this type of correlated noise as well as constant bias. The other issue also has to do with the sensors, that the manufacturing of these sensors, if you ask a manufacturer to give you a specification for specific accelerometers and you test 100 of them, you'll find very large variability, which means that you have to calibrate each sensor before you actually use it for navigation. Calibrating a sensor that costs $2 might cost you actually $5 or $10, which will not worth it, will not be applicable, will not be used by many of the smartphone companies. And therefore, fusion algorithm must be smart enough to calibrate the sensor on the fly to detect both the constant error as well as the random error properly. Otherwise, this will accumulate into large position error. So these are some of the challenges that actually limit the use of some of these sensors in navigation today. Solving these errors, solving these challenges, I think will enable some of these sensors to be used in navigation application very soon. We at Trusted Positioning Navigation, Trusted Positioning have really solved many of these issues. And I would like to share with you some of the performance of some of the sensors that currently used in some of the smartphones. I will start, before I do, also there is some other constraint or some other ways to improve the accuracy of the systems, some of which what we call velocity in the body frame. This velocity can be either coming from a vehicle, right, speed sensors, or it can be coming from an external signal such as GPS, some of which have to do with the motion itself. For example, non-harmonic constraint is a typical constraint we can use in a vehicle. In a vehicle, you're not expecting the vehicle to jump up or skid left or right, and you can use this as zero velocity constraint along the lateral velocity and the vertical velocity. Odometer can also provide us, for example, from vehicle, provide us with longitudinal velocity. All this type of constraint can be used in limiting the errors of the velocity of the accelerometers, and by limiting the velocity errors, you can also limit the position error. Again, because of the sensor errors that are typically highly nonlinear, you require that the algorithms that are being used are advanced algorithms and mostly nonlinear techniques such as unsended Kalman filter or particle filter. Because again of the sensor being very low cost, I'm expecting actually that in the next few years that you're going to see multi-sensor along the same axis. Instead of using only single accelerometer along the x direction, why not use 2 or 3 sensors? The cost is not actually a big issue for many consumer applications. I mentioned that many of the phone that I show as an example contains parameters and contains mags, and this gives you an extra degrees of freedom for the vertical direction, and this will give you an extra degrees of freedom for the azimuth, which is the major issue in many of the gyroscopes being used nowadays. Some other technique that can also use for improving the accuracy, backward smoothing. A backward smoothing is typically a post-mission technique. It's not a real time. However, there is many ways that you can actually implement backward smoothing over very short time interval, let's say 10 seconds or 20 seconds. And by doing so, you can actually improve the accuracy of the sensor or recalibrate the sensor on the fly. So this is some of the challenges and some of the solutions that can help in improving the accuracy of micro machine sensors. Having solving that, MEMS sensor will open actually many new applications beyond just navigation. Examples, mobile advertising, mobile device and user orientation, which is very important when we talk about location-based services, and tracking application. I hope Jalal was here to show him some of the potential for MEMS sensor for tracking applications. So I will try to show you a few examples. The first example was using the Samsung Galaxy Note, and this was actually for sport application. The following trajectory shows two trajectories. One red and which is GPS trajectory. The second one is the pure inertial navigation based on actually in GPS update every 1 minute. Every 1 minute, not every 1 second. You can see that actually the Samsung Note performance is very close to the GPS performance. And during this test, actually the phone was actually left to move freely with the user, so it was dangling, right? And in some scenarios that they're looking at the phone while they are actually running. So sports applications are actually some of the apps that will be enabled by the smartphones. Having of course sensor in the smartphone will allow us to not only have position but also velocity, orientation, counting how many steps, knowing the dynamics of the user, and thus improving the performance of athletes. Going to the major challenge with indoor and outdoor. This is another example, which is for the Galaxy Nexus, which have an InvenSense gyroscopes. I have a Bosch 3-axis accelerometer, Bosch barometer, and a Surfstar for GPS receiver. This test was done actually in Madrid, and the reason I want to show it is that you can clearly see in urban environment, GPS multipass is very severe to the limit that actually at some points, although there is an open sky, but because of severe multipass, the signal is the phone totally lost track to the limit that actually the GPS is here while I was actually doing this test. I was walking in the left-hand side of this building, and then going inside a mall, going out without GPS at all. And then if you look at the end, actually in this test we did not use the GPS till here. The final position was actually on the other side of the road. It's about 15-meter error after about 3-4 minutes without GPS. The next test was actually totally without any GPS or Wi-Fi for almost 9 minutes inside the building of our company. It includes multi-floors, stairs, going through an elevator up and down for a total distance of about 450 meters, totally indoor. And the maximum error in this case was about 6 meters, which is about 1.5% of the total driver's distance. So there is definitely very high potential for MEMS sensors to achieve many of these approaches, the level that has been mentioned early in the morning. And again, this is totally without any wireless technology inside the building. Also, there was a question by, I think, some of you and Jalal about the vertical. The nice thing about definitely MEMS sensors and self-contained sensors that they can provide 3D, not only 2D. And this just shows the same test here that I showed a few seconds ago. In this test, we took actually the elevator to the second floor and we stopped at the first floor. And you can see actually as soon as we go inside the building, of course there is noise, which is about 50 centimeters plus or minus. But as soon as you go to the elevator, we stop at the second floor, exact height almost 3.9 meters, going into the second floor, taking the average about 3.9 meters. So we can definitely use this sensor in estimating which floor and the elevation using MEMS sensors. I must say also in this test, we're not only relying on the accelerometers only on gyroscope, but also we have a barometer from the phone. And I forgot to mention that in this test, the phone was actually again left freely in the user hand, so it was dangling, right? And in many cases, it was actually the user was looking at it, looking at the phone, emulating that he or she was talking. So it was mainly, the typical scenario that a typical user do when using smartphones. Moving to the potential of this sensor for car navigation, and I know that I have car navigation. I believe that this sensor MEMS sensor will definitely enable many new applications such as assisted driving techniques and enhanced safety, which is demanded by many car manufacturers. I will show you two examples. One, the first one is what we call vehicle level MEMS sensor, which costs in total about $80. So in this test, we are comparing a system that contains a GPS receiver from Novatel, a vertical axis, one single axis gyro from silicon sensing, 3-axis accelerometer from SC Micro, and we're collecting the OBD2 speed sensor wirelessly from the vehicle. And this was done in Detroit and was compared against a $40K system from Novatel, which contains a Honeywell HG1700 IMU with a receiver. And the results from this system in post-mission, which means that the data has been collected and then processed in post-mission using DGBS, was about 1 to 2 meter, 95% in the test. You can look, of course, in the test itself, there is many areas that we don't have GPS at all. In some cases, actually, GPS was almost 100 meters away from the trajectory. And underneath that, you find the trajectory from the $100 unit that almost have about 5.9 meter, 95% of the time. I'll show you that through a quick video, and maybe I'll cut the video in the middle just for the sake of time. In the left-hand side, you have the vehicle. Oops. I'm sorry, it seems like I lost the link for the video when I moved the presentation here. But anyway, in this test, I just was showing the same test in 2D and also showing how the, again, $100 unit compared to the $40,000 unit. And again, in most of the cases was almost exactly the same. At the end of the test, again, there was about 5.9 meter as an overall accuracy. So the other question is that in consumer application, many of us take our car and park in a certain place. And when we park, of course, in, let's say, indoor, we lose GPS. So the question is, can we start from this scenario going without GPS as initial point? The answer is yes. And I'm showing that through a test that we did actually in our building. And this test was done totally without GPS using the Galaxy Nexus phone. And this test was about 7 minutes without GPS. We started indoor. We went outside. We took it in the car, and then we started driving. Of course, in this case, the phone was actually left freely on the seat of beside the driver, and therefore the unit can be actually moving freely in any direction. Of course, you expect that you will have an error, and you can see the error actually mainly in azimuth. We should actually be following this road, right? This small road here. And at the end, we should be actually this point, which is about 55 meters after 7 minutes. And the trajectory was about 2.2 kilometers. And in this case, about 2.5% of the travel distance. I must say that there is no speed sensor whatsoever has been used in this test. So the question is, how come in the phone performing in a vehicle at 2.5% while actually the phone was performing indoor at 1.5%, which is much better? I think the reason is that it depends on the fusion algorithm that you are using. We are using actually a number of techniques parallel to each other, not only BDR. We don't rely only on BDR. We rely on BDR, but also rely in the physics of the sensor itself in order to improve the accuracy. We can do that in pedestrian, but we cannot do that in the vehicle itself. So I hope with that I have shared with you some of the potential of these inertial sensors and the promising performance of them. And I'm expecting that actually this performance will improve as the sensor performance improve as well. I must say that I started working with MEMS sensors almost 8 years ago. With the first sensors was coming from ADI. Nowadays you can have the same performance for almost 100% of the cost of these sensors. Also the noise level of this sensor is being improved over the last 2 years, and I'm expecting that oxidal performance in terms of random walk and noise level will be also improving, and this will also lead to improvement in the navigation performance of these sensors. Thank you very much. So should I